Okay, everyone, give me just a second. I heard something fall over here. Hold on. Okay. How are you all doing? Doing okay? So I asked for you to have that quiz done for today, right? What I'm going to do, did I send a Dropbox for that? I don't know. Did I? No. Okay. Yeah. What I'll do is I'll just send a Dropbox for that after class for you to go ahead and just upload what you have. And if you had any questions on the quiz, maybe after we get through today, I will have answered some of the questions that you had, because we're going to do a few examples. So before I talk about the quiz at all, let's get through today's material. Now, you should have, up to this point, done the trig integral homework, at least the part of it from chapter 6, section 2, the first, it's the first like 36 problems.
Sir?
Yes.
I might have lost the question for the quiz, so is there a way you can like kind of put it up again? Because I wrote it down, but I lost it.
I don't recall where I put it. Let me see. Oh, it was from a test. That's right. You know what was it, everyone? It was the integral. It was the square root of something. Let me.
It was the square root of x squared minus 25 over x cubed dx.
Yeah, what he said.
That's it right there. Okay. I did send an email about this that I expected that you might run into some trouble on it. But like I said, let's get through today's stuff and then we will address this. I'll make the deadline for that like 5 o'clock, 6 o'clock this evening. That way you have some time to go back. And I'll also, at the end of class, I'll leave the Zoom session open if y'all want to stay in and talk to each other. I don't mind if y'all discuss the quiz with each other, as long as, you know, you're not just going and, you know, just to get the answer. That's just going to hurt you in the long run anyway. So, okay. So let's get, we did one example of trigonometric substitutions at the end of class last time. And so I just wanted to recap, you know, what a trigonometric substitution is, when we use it, and why we use it. So a trigonometric substitution is a substitution we make when we're looking at an integral where we replace the x or the variable, whatever the variable is, with some trigonometric expression, either a sine theta, a tangent theta, or a secant theta. And it all depends on what we see in the integrand. So what we're looking for, it says here, we use trigonometric substitutions when the integram has one of the square root forms from above. So we're trying to see somewhere in the integral, do we see one of these types of square roots? Either the square root of a constant minus x squared, or the square root of a constant plus x squared, or a square root of x squared minus a constant. If we see any of those, then we start thinking, okay, trigonometric substitution, all right? And then what we do is we make the substitution, and good things happen to the ugly stuff in the problem. The square root turns into a trig expression, and then what you wind up with at the end is a trig integral. And as long as you can solve the trig integral, then you're in business. So this is what I'm going to be picking up with today. We're going to work through, I'm going to try and get through 4 problems today. That's my goal. So let's see if we can do it, all right? So we're going to start off, our first problem here is this one. I want to find the integral of 1 over x squared times the square root of x squared plus 9. So in this problem, you know, of course, you're always going to want to do, you know, the thing that you do with all integrals. Is there a basic u substitution? Is there something easy I can do here? And if you look at this for a while, you'll kind of figure out that really there's nothing you can do. And the square root of x squared plus 9 should be making you think, oh, this looks like square root of x squared plus some variable squared. In our particular case here, the a would be 3, right? Because 9 is 3 squared. So what we need to do now is go to our formulas and determine which trigonometric substitution we're going to make. And in this case, we are looking at the blue case here because we have our variable squared plus a constant squared. So we're going to make a substitution that x equals a tangent theta. All right, so that's what I'm going to do. I'm about to make my trigonometric substitution right now. My trig sub is going to be x is equal to a, which is 3, and then tangent of theta. All right, so now that we know what the trig sub is, the question becomes, what does the square root of x squared plus 9 turn into, right? We can go and we can do it algebraically, like we can replace the x with 3 tangent theta and go through all the simplification, but I did that last time. So what we want to do is just go to our formula sheet, and I told you you could add these to your formula sheet last time, right? So make sure you add those. So what I know is that the square root thing is going to turn into a secant theta. So I'm just going to go over here and I'm going to write down that the square root of x squared plus 9 should be equal to a, which is 3, and then secant theta. So at this point, we can start substituting things, but you'll see right now that we're missing something. So right now we know x will be replaced with 3 tangent theta. We know that the entire square root of all this junk right here, that will be replaced with 3 secant theta. The one thing we still haven't resolved is what does the dx become, right? So the dx has to become something. So all we have to do is take our original trigonometric substitution and take the derivative of it with respect to theta. So we're going to get dx equals 3 times secant squared theta d theta. And that's because the derivative of tangent theta is secant squared theta. And the 3 just comes for the ride. Is everybody clear on this? Are there any questions up to this point? Okay. No? All right, now we just replace everything and we're going to have a new integral. So our new integral is going to be 1 over. Now x squared will be, again, that yellow part, 3 tangent theta squared, which gives me 9 tangent squared theta. So that's x squared times, and then the green part, the square root of x squared plus 9 gets replaced with 3 secant theta. And then I still have times dx, which is the blue part, which gets replaced with 3 secant squared theta d theta. And now what I have is a new integral, right? It's all in terms of theta, and it's a trig integral. So as long as I can handle this trig integral, I'll be okay. So I'm going to do some simplification first. I'm going to kill off these 3's. I have 2 factors of secant on the top and 1 on the bottom, so I'm going to cancel 1 factor of secant. And other than that, I can't really do any more canceling. I do have a 9 in the denominator, so I'm going to pull that out as a 1/9 outside the integral. I have the secant theta that was on top. I have the tangent squared theta that was on the bottom. And then d theta. Questions here? That's a trig integral, right? Just has trig stuff in it. So if we go back to what we learned on trig integrals, we do have methods to go after integrals that involve secant and tangent. The issue is here, though, that the secant and tangent are not up in the numerator together. If you look back on the kind of the steps we were doing last time, we always were looking for secant and theta to be together on the top so that we could like factor something out. Here, because the secant and the tangent are separate, or numerator and denominator separately, we can't use those steps. So what do, right? So I don't recall if I told y'all, I think I did, but just in case, what do we do if we have a trig integral and we're kind of like, can't really see where to go with it? What did I recommend you do? No?
Could we simplify to sine and cosine?
Yeah, there we go. Just make everything in terms of sine and cosine. And I'm not saying that that's always going to work, but sometimes when we get things in terms of sine and cosine, things just work out better. So I'm going to go 1/9. Okay, I'm going to rewrite secant. Secant theta is the same as the reciprocal of cosine, so I'm going to put 1 over cosine theta. And then over tangent theta, tangent squared theta, which is sine squared theta over cosine squared theta. And the reason that this is kind of a good step is that now you have a fraction over a fraction, so you can flip and maybe things will cancel because you got a bunch of sines and cosines. So all I'm going to do is turn that division into multiplication of the reciprocal. I forgot my squared on my cosine on the bottom. Sorry about that. Forgot that squared. So that's just algebra, right? Just flipping it up. And you can see there that one of the cosines cancels, right? You get one of these cosines will go away. And now our integral looks like this. 1/9 integral. We have just a cosine on top, and we have sine squared on the bottom. Okay, let's do a little Jeopardy moment here. So I'll give everyone an opportunity to think about how to go about that. And then I'm going to call on somebody. So let's do our little, maybe I'll just give you like 1 minute to figure out how you go about that. Do you need the Jeopardy background music, or you're okay with that? It's okay. I'm giving everyone 1 minute right now. All right, I'm going to call on, let's see, it says Michael Sandoval. I see Michael's here. Oh, there you are, Michael. All right, Michael, did you come up with a way to go about it?
Was to just integrate cosine because I separated it cosine times 1 over sine squared theta. That's the farthest that I got.
Okay, so you decided to rewrite this as cosine theta, basically like over 1 times 1 over sine squared theta?
Yes.
Okay, d theta. I didn't hear your audio in the beginning. Did you say that you did something, or that's it?
No, that's as far as I got, and I was just able to integrate cosine theta.
Okay, so you have to be careful, Michael, because remember we have multiplication here, right? So you cannot just integrate those separately, right?
That's right.
Okay, so I have no problem with what you've done here algebraically. I mean, that is correct. So when you think back when this class started, like the first thing that we learned was power rule. We don't have x to powers. Next thing was basic U sub. And then we did integration by parts, then trig integrals, and now we're not partial fractions, we're at trigonometric substitutions. So every time you get a new integral, you always want to start, like reset and just start everything over, like in your mind. So you look at this, is there anything you can do? So think about it, power rule's off the table, right? We can take power rule out, Michael? Okay.
Yes.
So what about basic U sub?
Yeah,
Do
we
you
could.
see something in its derivative?
Let me see.
So one of the things that I see a lot is students will overthink, just try and overthink this too much once they get to something like this. So think about, Michael, like cosine and sine, right?
Yes.
Those are like derivatives of one another, right?
Uh-huh.
So you could let u be sine here, or you could let u be cosine, and the derivative of it is also there. It's just you need to pick the right one here. And remember, you always want, whatever you pick, the derivative of it needs to be up on top and it can't be trapped, right?
Yes.
So what would you use for your u here then?
Let me see. Can we go with cosine?
Okay, so if you use cosine, the derivative of that is negative sine, right?
Yes.
But the sine is in the denominator,
Oh, that's right.
right? So you don't want that. You want it the other way around.
Mm-hmm.
So if we let u be sine, right, the derivative of that's just cosine. We don't have to worry about a negative, cosine theta d theta. And there is cosine theta d theta right there. You have that all on top, right? You could peel it off to the side if you wanted to. Like if you really wanted to see this, you could rewrite the problem like this. And now you can see that cosine theta d theta is exactly du, right? And you can replace the sine, just the sine, not the square, the sine with u. Okay, so this will just become 1/9 integral 1 over u squared du. And that, be careful, that's not, the antiderivative of that is not natural log, right? Because that's really like u to the -2. And the antiderivative of that, we're going to get -1/9 u to the -1 plus some constant. So all I did there was the power rule, right? I just did the power rule on u to the -2. And this, I could maybe rewrite one more. Well, I'll just leave it like that. I'll just leave it like that. We need to replace u though. U was sine theta. Now, we need to be careful here. In math, there's a couple of places where we have bad notation, and this is one of them. Because we're supposed to take sine theta, that's u, and we're supposed to raise it to the -1, right? Do not confuse that with the inverse sine function. What I'm saying is this. Sine with a little -1 of theta is not the same as sine of theta raised to the -1. The first one is the inverse trig function, inverse function. That's the notation we have for it. And this one is the reciprocal function. It's 1 over sine. Okay, and that's the one we have. We have this one. Okay, that's what we have. So when we write this down here, sine theta to the -1, we all have to be very clear with the fact that that's 1 over sine. All right, and 1 over sine is cosecant. Theta plus c. Okay, any questions up to that point? All right, so Christian, is Christian Garza here?
Yes.
Okay, so Christian, you following up to this point?
Yeah, I am.
Okay, so we're not done though, right? What's wrong with our answer at this point, Christian?
We have to get our antiderivative in terms of x.
Yeah, we have to get it back to x. And right now we're in terms of theta, right? Our answer has theta in it. So we have to go back to x. Christian, do you have any idea of how we're going to get this back to x?
Well, we have to use a reference triangle.
That's right. That's right. Good. So if you go back to last class, we did one example of this. So What we're going to do is we're going to go back to our original trig sub. Okay, you have to go back to the very first step where we did a trigonometric substitution. And we're going to write that equation down. X equals 3 tan theta. I'm going to put it right here. X equals 3 tan theta. Now, the reason we're using this equation is because this is an equation that shows the relationship that we have between x and theta. And since our answer has theta in it, and we want to turn it into something with x, that's the one piece of information that we're going to be able to use. So we divide both sides by 3 so that we can isolate the theta factor, tangent theta by itself. And then that's the part that we use to draw the triangle. So Christian, how comfortable are you drawing this triangle? If I label this side theta, can you tell me what the sides need to be?
Yeah, so the B side or the right side, that will be X.
Okay.
And then the adjacent side will be 3.
3, good. Okay, now Christian, do you know what the hypotenuse will be? How would you get it if you had to? Like, how would you go about it to try and find it? Let's call it H. for now.
The Pythagorean theorem.
The Pythagorean, right? We know that, essentially we have something like A, B, and C. So we know that A squared plus B squared has to be equal to C squared. So if we do that and work through this, we're going to have 3 squared plus x squared equals h squared, the hypotenuse squared. And we want to solve this thing for h, don't we? Because we don't know what h is. So this is 9 plus x squared equals h squared. And then we just take the square root on both sides. And that'll give us h. And we only take the positive answer because it's a hypotenuse. It has a length, so we won't look at that as being negative. So this side is the square root of x squared plus 9. Doesn't that happen? I mean, do you think it's coincidental that that's the form that we actually have within this integral? Do you think that's a coincidence, or will it always be that way, you think? It's
I
always
think
gonna
it'll
be.
always be that way because that's how the quiz came out to be too.
Yeah, I mean, one of the sides of your triangle is always going to be the form of the trig sub that you had. It's always going to turn out that way. So here we go. Okay, now Christian, good job. I'm going to move on to the next person. Sarah, is Sarah around today? I don't see Sarah anywhere. Okay, how about, is German around today?
Yes, sir.
Hey, how you doing?
Good in you?
Good. Are you outside today again?
Yeah.
It's nice out there, huh?
Yeah, it's windy.
Yeah, it is windy. Okay, so Dermot, why the triangle? Like, why did we do this triangle? What's the purpose of drawing this whole triangle out?
Honestly, for the triangle, I'm not sure, but
That's why I asked you, because I want to make sure that you know, and I'm expecting that a lot of people aren't sure why we're doing this.
isn't it from the expression? From
That's-
the tan expression?
From this expression or the answer?
No, the formula for tan.
Yeah, we're just using that. So here's the reason we do a triangle. Right now, just imagine you were like in a pre-calc class, okay? And I gave you this triangle. Couldn't I ask you what sine of theta is right now?
Oh, yes, sir.
Sine of theta would be opposite over hypotenuse, right? Are we all familiar with this thing, SOHCAHTOA?
Yeah.
SOHCAHTOA? By drawing the entire triangle and labeling all the sides, right now everyone in here should be able to tell me what sine of theta is, cosine of theta, and tangent. Because you have all the sides, right?
Yeah.
Now, if you know what sine, cosine, and tangent are, you also know what the reciprocals are. You know what cosecant is, you know what secant is, and you know what cotangent is, because it's just those answers flipped over, right?
Yeah. Basically,
So-
to find all the reciprocals.
Yeah, we can get all the reciprocals from this. But German, do you see that our answer right? Our answer had cosecant theta in it.
Yes, sir, I do.
And now that we have the triangle and we know that cosecant is the reciprocal of sine, all you have to tell me, German, is, you know, look at that triangle and tell me what cosecant theta would be off that triangle,
Yeah.
which would be, so
The
sine is opposite over hypotenuse, right?
yeah, so it would be hypotenuse over opposite.
Okay, good, over opposite. So you tell me what that is. What's the hypotenuse?
The x squared or the x
And
squared
then
plus 9
over the what side?
over x.
Over x, and that's it, right?
Yeah.
That is what cosecant theta is, and then plus c. Okay, so German, does that make more sense now, why we drew the triangle?
Yes, sir, it does.
Okay, good. So once you have that triangle, you can do anything you want with any trig function, that anything that winds up being in your answer, you'll be able to deal with it because you'll have the triangle that goes with it.
Yeah.
Okay, so that's our answer. And we could box that up and we move on. All right. Now we could also check this. Are we in the mood to check today?
Yes, sir.
I'm always in the mood to check my answers.
Quick question. Since the -1/9 is on the outside, like, would multiplying it into it also, like, you know, give you a correct answer? Like, would you deduct points if you like were to multiply those two together?
No, you can multiply them. I would just be careful on what you do. Like the 9 could go to the bottom, and the negative, you could just put it in front of the root. That's all you would do, is put the negative in front of the root. You wouldn't
All
try
right.
and move the, yeah, but that'd be right. So I think what you're saying is, you know, God, why does he keep doing that? That's weird. Could you do like negative square root of x squared plus 9 over 9x? Like that?
Yeah, that's what I was thinking, like condensing it.
Yep, that's fine. The only reason that I always leave my constants out front is because now that we're in calculus, we realize that when we do a lot of derivatives and antiderivatives here, and constants always seem to just come along for the ride. So I always leave them out front in case I ever have to take a derivative or integrate or do something again. I can always just have that out of my way. Okay, so I think I'm going to check this. So to check it, I just need to take the derivative of it, right? All right, so let me take the derivative. So here, perfect example. I'm about to take the derivative of this, and I have a -1/9 out front. It's a constant. It's going to come along for the ride. And then I have to multiply it times the derivative of all this. And that's a quotient. And so I'm going to do the quotient rule. That's how I'm going to take derivative. And I realize that the quotient rule is going to be a bunch of crap, so I'm going to make some room for it here. So the quotient rule says you take derivative of the top first. So the derivative of the numerator is the derivative of the square root of something, which is 1/2 times the square root of that something, times the derivative of what's underneath the square root, which is just 2x. And then I can't forget I have to multiply times the denominator. So that's the beginning. And then I do minus the derivative of the denominator, which is 1 times the numerator. And then the whole expression divided by the denominator squared. So that's quotient rule. And then I'm going to start cleaning things up. 2 cancels, 2 cancels. No, that's not a whole lot of cleaning up, but it is what it is. Okay, and then now what I have is I have these two x's together, so I have an x squared over the square root of x squared plus 9. And then minus 1 times that root is just that root, so I'm going to put the root here. And I'm actually going to put that root over 1, and you'll see that the reason for that on the next step, all of that over x squared. So I'm now going to try, this is what we call a complex fraction. So what I'm going to do is I'm going to try and put these two together. And so what I'm going to do is multiply the top and bottom by x squared plus 9, so that square root of x squared plus 9, so that I can have a common denominator. And that way I can push these two together. So when I do that, let's see, I'm going to have the x squared on the bottom I'm gonna have the common denominator here. And then my new numerator, let's see what that's gonna be. Well, x squared minus, and then when we put those two together, because they're both square roots and they're identical, you multiply them together, the root goes away. And so I'm left with x squared plus 9. I have to be careful to put that in parentheses because this negative will have to pass through. Do y'all see what happens to the x squareds when I do this? They're just going to go away, right? And then I still have a minus 9. So minus 9. So I'm going to have negative 1/9. And then I have a negative 9 over the square root of x squared plus 9. And then all of that is still over x squared, which I'm going to write as a fraction again. And the reason why I'm going to do that is because I want to look at it as a fraction over a fraction, and then be able to turn it, like flip it, bring it up as multiplication and flip it. So I'm going to get rid of that here and multiply by the reciprocal, like that. So here's where we are, negative 1/9. And then everything in brackets just becomes this. So times, I don't need the big bracket anymore. That over, I'm going to move that x squared to the other side of the square root. And my 9's go away. Oh, and my negatives both become a positive. So we're left with just 1 over x squared times the square root of x squared plus 9. There you go. Now, was that the original problem? That was. Yeah. All right, so what do you think? Eh?
A lot of steps.
Yeah, a lot of steps, right? Well, that only took us about, what, 30 minutes?
Okay, yeah.
All right. Well, the checking we didn't have to do. I always like to tell my students that if you want to get really good at taking derivatives, then check your answers in Cal 2, because that forces you to really prove that you understand how to apply all the rules and simplify to the point that you can get back the original problem. All right, let's look at the next problem. That was fun. Here we go. And you know what? I think, do we want to do this one? I'm going to change this one up a little bit. Not that I don't want to do this one. I want something specific to happen. So I'm going to change this to this instead. Because I know what's going to happen here and I want you to see it. All right, you ready? So A here is a constant. They're not telling us what it is, right? So we know X is the variable. We know X is the variable because of the dx, right? dx, that tells us that X is the variable here. So A is a constant. So we look at our forms, and this is exactly like this first form, right? It's exactly the same. So we're going to make a replacement. X is going to be A sine theta. And then the square root stuff is going to turn into A cosine theta. That's what I'm about to do. So X is going to be, here's my trig sub. I'm going to do X is equal to A, which is A, sine theta. The square root of A squared minus X squared. We know that that's going to turn into A cosine theta. And we're going to need dx. So dx is equal to the derivative of sine, well, the derivative of A sine theta, which is A cosine theta, d theta. Do not forget that d theta. You just took a derivative, so you need this d theta to be here. Any questions there? We can replace the square root here with A cosine theta. And we can replace dx with A cosine theta d theta. Notice that there's nothing in the integrand where we're going to have to replace an x, right? It's just, there's nothing there that we need to worry about. So those are the green and the blue are the only parts that we need to actually substitute in. So we have integral A cosine theta times dx, which is A cosine theta d theta. Now, since A is a constant, and I have A times A, I'm going to pull an A squared out of the integral. And then I have cosine times cosine, which is cosine squared theta d theta. All right. Jeopardy time. If you did your quiz, you probably recognize this. Hey, and just so y'all know, I don't keep a real good eye on the chat. So, you know, if you want to ask a question in the chat, then most likely it's your classmates that are going to answer. But feel free to interrupt, right? I've always told you, if you have something, you know, just ask. Just interrupt me while I'm talking. So, yeah, okay, let's take 30 seconds, and then I'm going to call on somebody. Is Jimmy around? Jimmy? I don't see Jimmy here. How about Maribel? Oh wait, you know what, Maribel? I'm gonna come back to you, sorry. Alex Silva?
Yes, sir.
Okay, there you are, Alex. All right, so Alex, did you come up with a plan for this one?
I mean, I was looking at the power reducing.
Yeah, power reducing. It's cosine square, right? We have an even
Right.
power cosine. So did you actually write down what this will become, or had you gotten to that?
Yeah, it was gonna be 1 plus cosine 2u over 2.
Okay, good. But don't forget the 1/2, right? The formula has
Oh,
1/2
yeah.
in front. And then 1 plus, you said cosine of 2u, right?
Yes.
But our variable is theta. So it's going to be cosine of 2
Oh,
theta,
theta.
right? And then d theta. Good. That's right. Good job.
Okay.
All right. I'm going to pull the half out. It's constant. Still have a squared. Okay, now Maribel. You ready to take the antiderivative of this, Maribel? Are you following so far everything we've done?
Yeah, I could try it out.
I'm sorry?
I could give it a try.
Okay, don't overthink it.
Okay.
You can do these piece by piece because there's addition between them, right? So the antiderivative of 1 would be
Yeah.
theta. Okay, so let me write this down. We have 1/2 a squared. Here comes the antiderivative, so I'm going to put this in parentheses, theta. Okay, then what? Antiderivative cosine 2 theta.
Will be 1/2 sine 2 theta.
Yep, plus 1/2 sine 2 theta, right?
Yes.
I don't know if you said 2 theta. It's hard to
Yes.
hear.
That's
Okay,
it.
plus c. Good. All right. We're there. Okay, we have an answer. We've taken an antiderivative. What we need to do now is get it back to x, right? So Maribel, I'll let you off the hook if you can tell me what I need to do next in order to get back to x. Like, what should my next step be?
I don't know. I think I'm good.
Right, this? I'm sorry, it's really hard to hear you, so I'm not quite sure what you said.
I think I'm good.
Okay, so this right here, right? This is the relationship we have between x and theta, our original trigonometric substitution. So that's what I'm going to write down now. X equals a sine theta. Give me a second, everyone. I've got to calibrate my pen. It's not pointing to where I actually am on the screen. Hold on.
Wait, will we do the triangle there? Could we?
Could you? What do you mean? Yeah, that's what we're about to do.
Okay, okay.
Yeah. Whenever we want to get from theta back to x, we're always going to need to bring in the triangle. And that means we're going to need to go to the original trigonometric substitution and write it down.
All
Okay,
right.
so there was our original. Then you want to solve, you want to isolate the trig function. So divide both sides by a, you get sine theta here. That's what the triangle is going to come from, right there. So right now, what we know is that when we draw our triangle, our triangle has to do with sine. Sine is opposite over hypotenuse. This is telling us that when we draw this, the x will be the opposite side, and the a will be the hypotenuse when I draw the triangle. So when I draw my right triangle, I label this angle theta. The opposite side will be x. The hypotenuse will be a. And then you have to do your Pythagorean to solve for this adjacent side. So I'm not going to go through the step here, but this will turn out to be the a squared minus x squared, which I told you was the form that we had, right? There it is. I can remember as a Cal 2 student, not knowing how my professor was getting this side and being confused. And if that's you, that's okay, but you need to get help on that. I'm not showing that every single time on purpose, because it's just a Pythagorean identity, a squared plus b squared is c squared, and solving for one of the sides. That is something that you should be able to do. And when I was in Cal 2, I'm not sure I was comfortable with it, but I was forced to get comfortable with it. And that's why I want to make sure you are forced to get comfortable with that too. All right. Okay, so we're here and we're moving on to trying to find the people who have the least amount of call-ons here. So, all right. Let's go with Christopher Ver, or is it Ver? Christopher Ver?
Either one's okay.
Okay. All right, are you following okay?
Yep, I'm following pretty well.
Okay. So for those of you who tried the quiz, this should look very familiar. All right, so Christopher, we haven't done anything like this before, all right? But I'm still gonna ask you, you know, what you could do. And if you don't know, you don't know, it's okay. What could you replace theta with? This is the tricky part. Like if it was sine theta, Christopher, if it was sine theta, you would just do, you look at your triangle and just do like opposite over hypotenuse, right?
Yes.
Okay, but it's not asking for sine of theta or cosine of theta or tangent of theta, right? It's asking for theta itself, like what's theta? And that can be confusing. But Christopher, I'm going to highlight the thing that you need to look at, and that's this right here. And just, I'm gonna ask you a question, Christopher. If I asked you to solve that for theta, do you know what you could do on both sides of that equation to solve it for theta?
Multiply each side by arc sine.
Okay, yes and no. You're gonna do arc sine on both sides of the equation, but it's not multiplication. It's actually, you're taking the inverse sine on both sides of the equation, right? So just the language, you're not multiplying by it, you're taking inverse sine on both sides, all right? So you take the inverse sine on the left, and then you take the inverse sine on the right. And Christopher did this because by putting the sine inverse with the sine, when you compose those two together, they kill each other off, and that spits out theta. And that's exactly what we want, right? We want theta to be replaced by something with x in it. So good job, Christopher. This is going to become 1/2 a squared parentheses arc sine of x over a plus, now I'm going to let Christopher off the hook because he did a good job on that. And by the way, y'all, I was watching one of my videos from last week. I usually don't watch them, but I was in my garage doing something and I accidentally hit YouTube on my Roku remote. and my YouTube channel came up and I just hit the video and I was watching it. And I want everyone to realize that, like, for some people I say good job and other people I may not say good job. Like, everyone who's here responding, y'all are all doing a good job, okay? It's right or wrong, doesn't matter. You're participating and that means a lot to me. And I really do appreciate those of you who are streaming your video. I told you, at the beginning of the semester, if you're streaming your video, I'm going to count that as bonus, as extra credit in the class. It makes a huge difference when I can associate your names and faces and stuff. So continue to participate and yeah, all right. So I think that was enough of a little pause to give Stephanie Vargas some time to think about what we're doing next. Stephanie? You there? Uh-oh. Stephanie, going once? Oh, your mic is, okay, I got you. Mic doesn't work, all right. All right, Yusuf is up. All right, so Yusuf, you're in charge of trying to get this 1/2 sine 2 theta in terms of x.
And would that be just 2 multiplied by x over a?
Okay, so yeah, this is the part that's troubling on this problem, this part, because what we have here is sine of 2 theta, right? We don't have sine of theta. We have sine of 2 theta. So I think what Yusuf is thinking is, can we just rewrite that as 2 sine theta? Like, can we pull the 2 out, figure out what sine theta is, and then multiply by 2? I think that's a natural question for a lot of students will ask that and think that maybe that's okay. But if you think about pre-cal, that was never allowed. You were never allowed to pull numbers out of trig functions. They just don't work that way. You can't, like, that 2 is not distributing in. If that's the way it worked, like, pre-cal would have been a lot easier. So instead, what you need to realize here, number one, Yusuf, you have to realize that your triangle is useless to you right now, because what we have in the expression is sine of 2 theta, and everything in the triangle refers to theta. So you have to look at this expression, sine of 2 theta, and go back to pre-cal and think about, is there a formula that allows us to take sine of 2 theta and rewrite it in terms of theta and not 2 theta? And we do have one. You have to go to your formula sheets. Now in pre-cal, this is one of the big formulas. So it's one of these ones that you want to...
The double angle, right?
Double angle formula, right? It's right here. And you can see it right here. Sine of 2x is equal to 2 sine x cosine x. That is the double angle identity or double angle formula for sine. And then you have another one for cosine and tangent. So that's what I'm about to use. And that's the part of the quiz problem that most people would get stuck on. All right, so before I do this, I'm going to rewrite this, okay? I'm going to rewrite this as 1/2 times, now here comes the sine 2 theta. It turns into 2 sine theta cosine theta. And fortunately for us, the 2's go away. The 2 and the half kill each other off, don't they? Like, we just kind of got lucky with that. And so now, Yusuf, remember, we're done taking antiderivatives, right? We're not even thinking antiderivative right now. We're just trying to figure out what's sine theta and then what's cosine theta, and let's just multiply them together. So now you can use your triangle. So what do you have for me?
I have x over a for sine theta.
That's your sine theta times?
The square root of a squared minus x squared.
Yep. Over
a.
Over a. Okay, there it is. Plus c. All right, that's it. We can clean this up a little bit. I mean, I could maybe put these a's together, make it an a squared, make that one big thing. And then, you know what? I don't know. No, I'll leave the 1/2 a squared outside. There it is. That's the antiderivative. Check it. I don't mind checking it, but let's do this. Let's go to Wolfram alpha. All right, because Wolfram alpha allows us to do this. I'll show you my screen in a second. Let me just get it up here. So what if we want to integrate the
So
square root?
Charles,
Sorry? Oh, minus x squared. We're integrating the square root of a squared minus x squared. So there it is. Well, it's similar. Do we have an x times the square root of? No, we don't, do we? Well, we have x times the square root of a squared minus x squared. Looks like they distributed this a squared through and killed off the a squared, so that's right. But then their part has an arc tangent. Do y'all see that? Arc tangent instead of arc sine. Now, why do they have arc tangent? I have no idea. The algorithm that they used, that's what they have. Now, we have the right answer because remember, this was theta, right? This in red was theta, and we found it by doing the arc sine on both sides of this equation. But you could have written this down. You could have written tangent theta, and just use your triangle. Tangent theta is this. And then do arc tangent on both sides. And that still would have given you theta, it just would have been a different expression. And that's what Wolfram alpha has. See, they have that expression now. So, you know, it's always easy for me, in these problems, it's always easy for me to see who is using a computer to get the answers. It's so easy for me to see because the computer does things that you would never do while you're working it by hand, right? So you have to be a little careful on that. I'm always a big fan of using computers and technology to check your answer, but not to depend on it to get your answer. All right, 2 down. 50 minutes, not bad, we're moving. Let's do this one. We're gonna let's take a minute. I'm gonna take a minute, just, yeah, minute and a half, just to let you look at it. And we'll just see, we'll take volunteers to see if anyone can figure out how to even start this problem. All right, any volunteers? Or does anyone just want to tell me how they feel when they see this problem? Go ahead, Ross.
The first thing I thought of was taking the 4x squared plus 9 to the 3 halves and making it the square root of 4x squared plus 9 cubed. I don't know if that's right or not, but it made sense in my head.
That's perfect.
But then would that cancel out the cubed on top with the x cubed?
Mm-mm.
Okay, that's where I wasn't sure, so I just wanted to double check.
Yeah, but that's a good first step. is to realize that raising something to the 3/2 is the same as taking the square root of it and then cubing it. And by doing that, you're starting to get closer to a trig sub form, aren't you?
Yeah.
Now, the problem we have, though, is that in the forms that we have, notice that on these formulas, that you always have just x squared. In other words, it's like a 1 in front of these x squareds. Do you see that? It's like a 1. And so we don't have that here, do we? We have a 4 in front of our x squared. And that means that the formula will not work the same. We have to have that be a 1. So before we do anything, I need to get rid of the 4. So let's go through the algebra of how to remove the 4. So what I'm going to do is I'm going to, sorry about that, hold on, let me go shut those animals up. Okay. Hey, what up? My wife likes little dogs that bark a lot. Okay, so I factored a 4 out, right? You see this? So obviously I can pull a 4 out of 4x squared, but since there is not a 4 in the 9, I have to rewrite the 9 as 9/4. And all you have to do to check algebraically that this is the same is to just think about what would happen if you distributed this through, right? You would get the same expression as we had up top. So that little algebra thing, it is an algebra thing, but it's something everyone here should be aware that they can do. All right, is there any questions on that algebra? Okay, watch what I do next. Here's what we have. We have the square root of 4 times the square root of x squared plus 9/4, then all of that cubed. So all I did is I split we had a product underneath the root. See, that's a product right there now because we factored the 4 out. And when you have a product under a root, you can split it into 2 square roots. So I did that. And now what I can do is I can apply the cubed here to each of these. So this becomes, well, the square root of 4 is 2. So this becomes 2 cubed times, I don't like writing it that way. Let me write it this way. Okay. Any questions there? That's all just algebra, but you need to make sure you're comfortable with it. So I pulled that out, and basically I'm going to get an 8 there in front, right? 2 cubed is an 8. And so I'm going to wind up just pulling that completely out of the integral on the bottom. So I have 1/8 integral x cubed on top, and on the bottom, I have the square root of x squared plus 9/4, that whole quantity cubed dx. Okay, good. Here we are. Now we have the form that we need to make the trig sub. And how about Cheyenne? Is Cheyenne here? I see no Cheyenne. How about Jorge? No, Nick. Nick Weens? There's Nick.
Oh,
How's it going, Nick?
it's going.
It's going. All right. You following me?
Yeah.
Okay. What form do we have? When we look at our formula sheets, do we have 1, 2, or 3 here?
Mm,
Here it is. Oh, yeah. No. Here it is, right here. So, which of these forms do we have?
we have 3.
So you see something squared minus something squared. here?
Oh, no.
Okay. So we have
It's 2.
2. Okay, so what is the trigonometric substitution we're going to make?
X equals A tan theta.
Good. Okay, so let's do that. We're going to do x equals a tan theta. Everyone clear with that? Okay, so here it comes. Here's my trig sub. I'm going to do x equals, I'm just going to write it down so I have it here, a tan theta. Nick, this is a little bit tricky, but do you know what a is here?
Can you give me like 10 seconds?
Okay.
A is x over tan theta.
Oh yeah, okay, so all you did, you just took this and solved that for a. That's not what I'm asking. I'm saying what is the constant that we have in this problem? Are you not sure?
I'm not sure.
Okay, someone want to help?
Would it be 9/4?
Okay, so that's a squared, right? That
Oh, so
number is
it would be the
squared.
square root of it.
So it's the square root of that, which is just 3/2, right? You just take the square root of each, the top and the bottom separately. So for us, a is 3/2, and then tan theta. So Nick, what you did is you just took this and solved it for a algebraically, which is not what we want, what I was asking for. What I was asking for was, if this is the form we have, right? If we're going to be using formula 2 here, then you need to figure out what a is, right? And a is, if the number that's by itself is a squared, so you have to take square root of that to get a. All right, now what do we know about the square root of x squared plus 9/4? And I'm going to ask who's here on my list now. See, Coleman, you're up.
So that is going to be equal to a secant theta.
Okay, so a here is 3/2, and then secant theta. And you're just getting that off the little formula sheet, right?
Yes.
Okay, and then we're also going to need to know what dx is. So do you want to tell me what dx is, Coleman?
Be a secant squared theta.
Okay, so 3/2 secant squared theta d theta. Good. All right, so now let's just think about what we've got here. We've got, let's see, x, we're gonna have to cube it, right? And this is what x is, so we're gonna have to cube all that. And then we have the square root of all this crap here, right? And all of that is gonna turn into this, but we still have to cube that also. And then we also have dx, which is gonna become this. So we got a lot of stuff to plug in, don't we? Okay, let's do it. So this becomes 1/8 integral. Now, I have to cube x, right? I have to cube it. So that means I have to do the 3/2 cubed and then the tangent cubed. I'm gonna write it this way, 3/2 cubed. Now I realize everyone could figure out what that is. That's 27/8, but I'm just gonna leave it like that. You'll see why in a minute. Tan cubed theta over, okay, the square root of everything turns into 3/2. Yeah, we're cubing it. So cubed secant cubed theta. Does anyone have a question on what I did there? That's the part in green cubed. You can't forget that we have a cube there. We still need the dx, which is going to be 3/2 secant squared theta d theta. All right. Now, do y'all see why I left it as 3/2 cubed? Because I could see that this was just going to go away. I mean, if you would have wrote 27/8, it would have been fine. They still would have gone away. That other 3/2 doesn't go anywhere though. So I'm just take it out of the integral. And so now what I'm going to have is not a 3/16 integral So I just multiplied 1/8 times 3 halves. Let's see, secant wise, 2 of these secants cancel out. And so I should just have 1 secant left on the bottom and a tan cubed on top. All right, how are y'all feeling so far? It's all right? Okay, Coleman, let's see, Alex, oh wait, no, hold on. Ross, did I call on you? Ross, you've already responded though. You wanna respond again, or? It's up to you.
Sure. What was the question?
Yeah, I hadn't asked a question yet.
Okay, cool.
Yeah, what now? What would you do?
I mean, you could make tangent into like sine and cosine since you have secant on the bottom.
Yeah, I like that idea. I like what we did kind of earlier. We've got tangents and secants split up, numerator and denominator. So let's just get everything to sine and cosine.
Yeah.
So we'll go sine cubed theta over cosine cubed theta. That's tangent cubed. And then over secant theta, which is 1 over cosine theta, d theta.
I have a question.
Yes.
On the tan cubed, we'll be able to use the identity on it. The power of tan is x is odd. Instead of going to the sine and cosine.
I'm not sure what you mean identity. You mean like the Pythagorean identity?
No, on the paper you give us the little sheet. It says the power of tan x is odd. Save a factor of secant x and tan x and use tan squared x equals secant squared x minus 1.
Oh, okay, yeah. If it was tan squared, we could, but we can't for tan cubed. The formula only works if it's squared.
All right, thank you.
Mm-hmm. All right, so now I'm going to flip. So I've done this, I think, 3 times today. I'm flipping that up to make it cosine theta over 1 instead. And then one of these cosines cancels out and makes that a cosine squared on the bottom. So we should have on top a sine cubed. And on the bottom, we should have a cosine squared. D theta. All right, it's Jeopardy time. You've got a minute and a half. That's a minute and a half just to figure out what the next step is, not to finish it off. Can you all hear that?
Sir.
All right, that's good enough. All right, I'm debating if I should call on somebody or let me just call on someone. This is fun. All right, Jorge.
I actually have a question.
Oh, go ahead, Nick.
This does pertain to the next step. Can we just turn the equation into 3/16 integration of sine cubed theta over 1 times 1 over cosine squared theta.
Wait, say it again. Sine, what do you want to do with it?
Like kind of like what we did in the last step.
Mm-hmm.
Like just put the sine cubed theta over 1 and then multiply that by 1 over cosine squared theta.
Okay, yeah, so I think what you're saying is this. Could we write like this? And then 1 over cosine squared theta, right? Like that?
Yeah.
Yeah, I mean, you can do that. That's, I mean, algebraically, that's correct. My question would be, then what? Like at that point, then what do you want to do? Like, how did that help you? You can't
Could
do them
we
individually.
use substitution?
Okay, what would your U substitution be?
U can equal sine theta.
Okay, so if U is sine theta, the derivative of that is cosine theta, but that's down in the denominator, right? You don't really want that. You don't want your du to ever be down in the denominator. You don't want it to be trapped under a root or even squared or cubed or anything like that. You always want your du to be something that you can peel off to the side. So I'm kind of okay with what you did here, and I'm okay with you wanting to do a U substitution. I'm just not quite sure I agree with the U substitution.
Oh, Professor.
Yes.
Could we go back to what x equals to?
At this point, before the integration, no. Because if you do, you're going to wind up with the original problem.
Oh, okay, okay.
Yeah, you always want to do back to x after you do the integral.
All right.
Can I try taking a jab at trying to figure out what the next step is?
Sure, go ahead.
Would you peel off a sine to get sine squared over cosine squared times sine?
Okay, let me do that. Let's see if that takes us anywhere. You're going to peel one sine off the top.
Mm-hmm.
And I'm just going to write it out here to the side.
Yes.
All right. Okay, yeah, now what?
This is where I was a little bit confused. I thought I'd do a U sub and try to figure that out. But like I was thinking I'd do negative cosine and then the derivative of that would be sine. So I could just get du as the peel off. But the only issue is that it's a little bit, I was kind of stuck on that part.
Okay, so I agree with the substitution of u being cosine theta. Don't worry about the negative.
Okay.
Just u be cosine theta. The derivative of that will be negative sine theta, but then you're just going to multiply both sides here by negative. So you've got sine theta d theta. So you've got this right here, and you can replace cosine with u. So the only thing left to deal with is that sine squared up top, because you can't use any of this. You've already used it. So you want to try and see if there's a way to get this sine squared in terms of cosine.
Professor.
Yes.
Oh, well, I don't know, but if you were to turn them into tangent squared theta and then use the power reducing, could that help?
Oh, okay. You mean on this, turn this into tangent squared?
Yes, sir.
And then from there, use the power reducing formula. You could do that, but the problem is you're then going to have this sine theta d theta on the outside. So when you do the power reducing on this, when you do, I'm going to do PR. When you power reduce that, notice in the formula for power reducing that you actually get a double angle. So on the formula right here, when you do this power reducing, oh wait, you know what? No, that one doesn't double your angle. Simplifies. Sorry, no, I'm looking at the wrong one. Yeah, so if you did that, we don't have a power reducing for tangent written on this formula sheet. You would have to do this on top and this on bottom. Just ignore what I said up here. I was doing a double angle, sorry. If you did that, you would now have a 2 theta in the problem instead. And then on the outside here, you'd have a theta, and that would be a problem. I mean, we're basically here. I mean, we're almost to the point. We have this blue, this green, just sine squared. You need sine squared to be in terms of cosine.
And that just be 1 minus cosine squared theta?
Yeah, I
use
just
your
put them
Pythagorean identity.
distinction.
Just use your Pythagorean identity, right? Sine squared is the same as 1 minus cosine squared. And then over cosine squared. And then sine theta d theta. And now let's do the u substitution. Let's just plug u in, right? Because we have all the pieces we need. Everything in green is going to become a u, and then all the blue is going to become negative du, right? Negative du. So since it becomes negative du, I'm going to pull the negative out. Integral 1 minus u squared over u squared du. Now what? Can we handle that?
Separate the fractions.
Yeah, just split it up. We have 2 terms in the numerator and 1 in the denominator. So we can split this up as 1 over u squared minus u squared over u squared, which is 1. I'm about to use the power rule, so that's why I'm bringing that 1 over u squared up. Again, it's not natural log, right? It has to be 1 over u for the antiderivative to be natural log. So we're going to use our power rule. So now it's time for the antiderivative. So 3/16 in front, I'm going to have negative u to the negative 1 minus u, not du, plus c. So the antiderivative of u to the negative 2 is negative u to the negative 1, and the antiderivative of 1 with respect to u is just u. That's this. I think I'll distribute my 3/16 through. All right, what was u?
Cosine?
U was cosine. So cosine to the negative 1 is the same as not our cosine, right? It's not inverse cosine. It's 1 over cosine. And what is 1 over cosine?
Secant.
Secant theta. And then plus 3/16 u, which is cosine theta, plus c. All right. Is Jorge here? Yes, I see Jorge.
Yeah, I'm here.
It's going okay, Jorge?
Yeah, I'm doing good.
Okay. So what now?
Then you have to do the reference triangle.
That's
Make
right.
a
reference
32x.
triangle. So what's the thing I need to write down here on the side to get my
So
reference
the
triangle?
x equals 3/2 tan theta.
3/2 tan theta.
Yeah.
Okay, so once you have that, Jorge, what do you do?
And you have to take the 3/2, move it to the other side. So it's divide 3/2.
That's right.
X.
I'm going to divide 3/2. Oh, go ahead.
No, you good. You could talk.
Okay, so instead of dividing by 3/2, I'm going to multiply by 2/3. It's the same thing, right?
Yeah.
But it gives me 2x over 3 on that side. And the reason I like that is because now I have tangent is opposite over hypotenuse. So I have an opposite side and I have a hypotenuse. It's kind of easy for me to see what it is from here. All right, good, Jorge. Now, opposite side, Jorge, is 2x.
Yeah.
Did I say hypotenuse? I did say hypotenuse. I apologize.
Yeah.
Tangent is opposite over adjacent. And so we have the opposite and the adjacent side. So this should be a 3. Jorge, what's the hypotenuse then?
That would be this one's gonna be 4x squared plus 9.
4x squared.
No, I mean the square root.
Yeah, square root 4x squared plus 9, right?
Yeah.
All right. I'll let you finish it, Jorge, since you've gone this far. I'm going to get the answer. Can you tell me what secant theta is, Jorge?
Secant is so it'll be 4x squared plus 9 square root.
Mm-hmm. Over?
It'll be 3.
Over 3? Okay, and then plus 3/16.
It would be 3 over the square root of 4x squared plus 9.
There you go.
Let's see.
Good job. Okay, so there we go. Does everyone understand where those pieces came from? Secant theta is hypotenuse over adjacent. Cosine theta is adjacent over hypotenuse. So this is your antiderivative. I guess we could kill off those 3's and we could probably multiply that 3 and that 3 to get a 9, but pretty much we're there.
I had a quick question about this problem.
Mm-hmm.
Back earlier when we did the trig sub where we did x equals 3/2 tangent theta, I was a little bit confused about how we got dx equals 3/2 secant squared theta. Like I know you did square root of x squared plus 9 over 4 equals 3/2 secant theta.
Mm-hmm.
Were you doing like tangent squared equals 1 minus secant squared to figure that out, or
For the green or the yellow?
for the yellow?
For the yellow, all we did was took the derivative of this. So
And okay.
constant comes down, right? Derivative of tangent of theta is secant squared theta.
Secant squared.
That's
Okay.
how we got the yellow.
So how'd you do green then? Did you substitute x for the square root of x squared plus 9 over 4?
Well, the green, I just used the formula sheet because that's kind of a shortcut. If you wanted to do it, if you actually wanted to figure out why this is equal to this, you would have to write down the square root of x squared plus 9/4. You would have to replace x with that right there. So you'd have to put that in for x. So square it, it becomes 9/4 tan squared theta, but then you still had 9/4. And then you'd pull out a 9/4 out of each one of those. And then you'd use the Pythagorean identity to replace that part in blue with secant squared.
Oh,
And then you
okay.
do the square root. But see, I don't want you to have to do that every single time. That's why I'm giving that to you on the cheat sheet, on the formulas. That I told you you could write that in. Because
Right.
that's going to eat up more time on the test that I don't necessarily want you to have to do. All right?
Okay, that
That's
makes
where it
sense.
comes from. That's where it comes from.
Thank you, sir.
Uh-huh. Okay, so we got through it. That took us almost 30 minutes. All right, try and squeeze one more in here. I don't think we're gonna finish this one, all right? So this might turn out to be a take home, you finish, turn in for a quiz grade. And here it is. Just let me think about it because I want to do something a little different than what's here. Hold on, let me just think. 1 over square root of 5x squared plus 2x minus shit. Okay. All right. All right. Cross your fingers. No, this will work. I mean, okay. I really like this problem. You'll notice right away that it's not one of the forms that we have, right? Because it has that 2x term. Do y'all agree that if we had this, we would do it just like the problem before? We would pull a 5 out, right? We'd first pull a 5 out to get a 1 on that x squared, and then we get that, you know, and then we would do our trig sub. But because we have a 2x in the middle there, we can't do this, right? We can't. Because even if we pull a 5 out, we're still going to have this thing in the middle that makes it where the form doesn't look right, right? All of these forms, none of them have an x term in the middle, none of them, right? So, you know, what do we do, right? So what we're going to do, all right, the first step to this problem is to complete the square. All right, so that should ring a bell. That's something you do in college algebra. You complete the square. Let's do a quick poll. How many of you I'm not asking you whether or not you remember how to do it, but yes or no, you know you've done completing the square at some point in your life. All right, so that's most of you, okay? There's like 1 or 2 that are saying that you don't think you've ever completed the square. I bet you have. All right, so what we do, okay, this is kind of a separate problem right now. We're just going to take the quadratic expression that we have underneath the root without the square root on it, and we're going to try and complete the square. And the whole idea behind completing the square is this. We're going to do something so that at the end of it, we're going to have something squared minus something squared, all right? This thing's going to have some x's in it, and this thing is going to be a number. That's what completing the square does. And what's good about that is that if we can get this thing to look like this, then it'll kind of be like the form that we need to use the trig sub, because remember, all of that's under a square root. All right, so we have to do that first. Okay, let's see if we can do it. Does anyone remember the first step to completing the square? The first thing you have to make sure you have.
Move the 9 over? Oh no, it's got to be a 1 in front of the x squared.
Okay, you have to have a 1 in front of the x squared. You can't have a 5. So the first thing I'm going to do is factor a 5 out. Now, I can factor a 5 out of the x squared, but none of the remaining terms have 5s, do they? So I have to still pull the 5 out of the 2 by writing as 2/5 x, and I have to pull a 5 out of the 9 by writing as 9/5. Now, we did something very similar to that a minute ago, didn't we? Okay, that's equal to that. Any questions on that step? If you don't believe that that's true, just distribute the 5 back through, and you're going to get back the expression above, right? Okay, now that we have that, we have a 1 in front of the x squared. What do we do next? I'm going to say this. It's almost okay if you don't remember. All right. I'm actually think you might be better off if you don't remember. And the reason why is because the people who do remember, usually their next step to me is something like moving something to the other side, or doing something like adding something to both sides of the equation. The problem with that is we don't have an equation. Does everyone see that? We don't have an equal sign. So what I'm going to do is just take you back to college algebra quickly. When we're in college algebra and we're trying to solve an equation, okay, we're usually trying to solve this. And we're taught that there are different ways to solve a quadratic equation. We can factor it, maybe. Sometimes it factors, sometimes it doesn't. And then we can complete the square, and then we're given the quadratic formula. We're all happy about the quadratic formula because you can solve any quadratic with a quadratic formula. But the big deal in this is that you have an equation. You have it set equal to 0. And when you have equations, you can do things to both sides. But now here we are in Cal 2, we're looking at an integral. We have an expression, not an equation. We have an expression we're trying to complete the square of. And since we can't just throw an equal sign in here, it's no longer the same thing. An expression and equation are totally different things. We can still complete the square, but the procedure, the technique is different. And so that's why I think it's useful. Like if you don't remember completing the square, it's actually going to maybe help you right now, because you're forced to do it this way. All right. All right. So here's what we do. Once you've got a 1 in front of the x squared, you look at the number that's in front of the x term. Okay. You identify what that number is. Now for us, that number is 2/5. So I'm going to write that number down over here, 2/5. What we do to that number is we divide it by 2. Okay, every single time we do completing the square, we're going to take the number in front of x and we're going to divide it by 2. So dividing by 2 is the same as multiplying by a half. Do y'all agree? Dividing by 2 is the same. Okay, so I'm going to take that number and multiply it times a half. And the 2's cancel, and we multiply straight across, I get 1/5. Going to box that number, put a star next to it. That's a special number, all right? We're going to use that number in a little while. After you get that number, the next thing you do is you take that number and you square it. So you square the top and you square the bottom, and we're going to box that. That's the second special number that we get. So every time you complete the square, you're always going to have 2 numbers that you work with. The first one you get by just taking the number in front of x and taking half of it. The second number you get by taking that number you just got and squaring it. All right. Now this is the part in a college algebra class where your teacher usually told you take that 1/25 and add it to both sides of the equation. Okay? We don't have an equation. So here's what we're going to do. We're going to do something that's considered to be a pretty advanced idea in mathematics. We are going to realize that right here, after the 2x, there is a 0. Okay, so we're realizing what we refer to as a hidden 0. There's a 0 sitting next to that, right? If I take 2/5 x, I add nothing to it, and then I subtract 9/5, that's the same as what we had before, right? But that 0 on the next line is going to be written in a very clever way. We're going to rewrite it using that second special number. So what I'm going to do is I'm going to, instead of writing +0, I'm going to write +1/25 and then -1/25. That's still 0, isn't it? And then I still have here -9/5. 9/5, yeah. Hidden 0. Now, why am I doing this? What does this procedure get us? Well, if you follow the procedure correctly and you do all this, the first 3 terms are guaranteed to factor. The first 3 terms are now what we refer to as a perfect square trinomial. And so I know that my next line will look like this. Everything in green there is going to turn into something squared. And the something that it turns into is x. Does anyone know what comes here?
+1/5.
+1/5. This is where that first special number comes in. +1/5. Okay, so let's in case you don't believe what we're doing, if I take x +1/5 and I square it, I multiply it times itself, and I do this FOIL. And I collect these like terms together, you'll see that this matches this. Right? Those first 3 terms are guaranteed. That's not a coincidence. By design, this is what completing the square is all about. Now, what's still left and what we still have to resolve is this -1/25 -9/5. We have to still put those together now. So we have to get a common denominator between those, right? So we multiply this second fraction by 5/5. So that fraction becomes, what does that become? 25 and 5 is what, 45/25? That's a 45. That didn't get much better. 45/25. Now, put those together, that should be -46/25. Do y'all agree? All right. That's completing the square done on an expression. All right. So you might ask yourself, like, why are you taught to do it both sides of the equation, right? In college algebra, why aren't you taught this way? And really, it's because you're dealing with equations in college algebra. So you have the luxury of both sides of the equation. When I teach college algebra, which I haven't taught it in many years, when I teach college algebra and I teach completing the square, I always show them this way. I never show them both sides of the equation because you don't always have that. Like later on in calculus, like you don't have it. So you've got to have a method that would work in both scenarios. And that's why this one does work. All right, we still got 5 minutes. Let's see where we are in this problem. I'm going to get rid of some stuff. I hope you don't mind. I'm going to get rid of this. And let's see where we are. We are at integral 1 over the square root of. Okay, now underneath that square root is all of this, right? That's the quadratic rewritten. So I'm going to put the 5 here, parenthesis, then another parenthesis, x plus a fifth squared, then minus 46 over 25. That's not 46, that's 45, 46 over 25. And then close that parenthesis, and then dx. Now I have this is multiplication right here underneath the root, so I can split that into 2, can't I? I can split that into 2 roots, and I'm actually on the next step going to pull that square root of 5 out. Now, unfortunately, it's not a perfect square, so I have to just leave it as square root of 5. Okay, 4 minutes, 4 minutes. Is this starting to look a little bit more like you can use trig sub? A little bit more? I'm going to do one more thing. I'm going to make a quick u sub. I'm just going to replace x plus 1/5 with u. This is a basic u sub, not a trig sub. Du then would just be dx. Everywhere I see an x plus a fifth, I'm going to replace it with u. Everywhere I see a dx, I'm going to replace it with du. And when I do that, this integral becomes this. See, x plus 1/5, that's u squared, minus 46 over 25, and then dx becomes du. Now I have something I can use trig sub with. Do y'all see that? Now I'm using u in the problem, not x, right? I'm using u. So we would now make a trig sub. And instead of writing x equals a sine theta, or x equals a tangent theta, or x equals a whatever we're going to do, we're going to do u equals, and then whatever the trig sub is. Do you know what a is? A is the square root of that number, isn't it? Okay, so if I were writing down what a was, I would say a is the square root of 46 over 25, which I would write the square root of 46 over 5. I'd just do them separately. And I don't know, I'd probably just leave it like that. Okay, so let's say that I'm going to make this a do-at-home quiz problem. Let's say for next time that you finish this problem out. You need to figure out what the correct u sub is, or sorry, trig sub is. You need to turn it into a trig integral. You need to solve that trig integral. You got to get from theta back to u and then u back to x. Okay? All right. How do y'all feel about this? Yeah? I mean, this is now like, this is a legitimate math that we're doing now. This is legitimate calculus too. If you look at our schedule, we are slated for an exam on October 14th. So we still got a ways to go here. We're just finishing up. Today we're officially going to say we're done with trig sub. All right, there's no more. I mean, now it's just you got to go practice, do the homework. I think the good news is that we can see light at the end of the tunnel here. 6-4, I think, is equally as difficult, if not slightly more difficult than trig sub. So we got one more really tough section, 6-3. Did I say 6-4? 6-3 is tough. 6-4, don't even worry about it. That section we're not even going to have problems from. So 6.3, after we get past 6.3, it kind of eases up a little bit. And we're kind of like, we can take a breath and we can be like, okay, let's get through the rest. We'll have our second exam. Then the first part of chapter 7, well, chapter 7 is all, I think, stuff students normally do okay with. It's not till we get to chapter 8 where things start to get pretty bumpy again. All right, so you're almost there in terms of getting through the techniques of integration. So do your homework and yeah. Any questions or comments or anything? Do your homework. This is probably the most important section that you, this one and 6.3. It's yeah, it's heavy stuff. All right. So I'm going to send you a link to a Dropbox for today's quiz that was due today. I'll send that out right now, and then you can drop your quiz in there by like 5 o'clock, 5 or 6 today. And then the quiz that I'm giving you, that problem to finish, that'll be due next time, and I'll send a different Dropbox on Wednesday or something. All right, everyone. I guess that's it. Do you want me to leave the session open if anyone wants to talk about things?
I have a question.
Yeah.
Where's the quiz you were talking about that's due today? Or what do you mean? Because I don't see anywhere on Canvas.
No, at the end of class last time, I showed everyone a problem from an exam that I gave, and I asked everyone to do that as a take-home quiz.
Oh, okay. Okay, so that one's due today?
Today, yep.
Okay, thank you.
Now that we've covered what we covered today, you should be able to do that one. Like,
Wait,
okay.
Professor, I had a quick question about that problem.
Yeah.
The way that I wrote it down from last week, I had the whole thing in a square root. So like x cubed was in the square root too. Is it supposed to be in the square root or not?
Mm-mm.
No? Oh shoot. Okay, I did it wrong then.
Yeah. Yeah, if it was all underneath the square root, if everything was underneath the square root, I'm not quite sure you'd be able to do it.
Yeah, I was stuck on it. I muddled my way through and came up with something, but I think I have to redo it.
Yeah. It'll work out nice if you do it the way it's written.
Yeah, I could see it'd be a lot nicer. Thank you, Professor. Appreciate it.
No problem.
Also kind of related to the question, because sometimes I have a hard time starting it. Where would you say is a good starting point for this one?
To recognize that it's a trig subproblem because of the square root. Is that what you're saying? Is that what you're asking me?
Sort of, but the denominator is sort of throwing me off. Like just looking at it, it's like I don't know how
don't worry about the denominator. So with trig sub, you're kind of saying, okay, if I see a square root of x squared minus a squared, or square root of x squared plus a squared, or square root of a squared minus x squared, if I see any of those three forms anywhere in my integral, trig sub is on the table. So you make your substitution, then you figure out what everything is. Don't let the other stuff around it freak you out. Like that's all going to get replaced with stuff with trig. It's all going to be replaced with trig stuff, and then things will start to cancel and simplify. So does that make sense, Peggy? Like don't get too locked up on other things within the integral.
Yes, sort of. Also, is like the formula sheet that you were kind of sharing, is that also like on the formula sheets that we're allowed to print, or like where is that?
This right
like
here.
That one.
Yeah, okay, so if you go to our formula sheets, right, in Canvas, there are, I think, 4 different things that in our formulas folder that you can have. This first one is just the standard pages from the back of the book. The next one is the trig sub formulas. So this shows you the steps on how to do sine and cosine together, tangent and secant together, and at the bottom of it is the trig sub formulas. And then I told you you could add this in, you could write these into your formulas, that was okay with me. And then we have series tests, which we haven't covered yet. And then we have Maclaurin series. So those are 2 more sets of formulas we'll be using later. Does that answer your question, Peggy?
Yeah.
It's all in Canvas. Any others?
Are you gonna send the Dropbox link through Canvas, or will it be through the chat right now?
No, I'll send it through Canvas because I don't have it set up yet. So
Okay.
I'll create the file. Oh, why am I not signed in? What? Okay, I'm gonna have to get, I don't know why I'm signed out. I'm gonna have to sign back in and get this all set up. So expect it in the next few minutes. All right. Y'all want me to leave this open? I can leave it open. I've got office hours that start at 1, so I'll have to shut it down by 1. But if y'all want to hang out here, I'm gonna step away. And stop the recording.